Okay, this video is a homework help video corresponding to Unit 9, Objective 6. This homework help video, if you're matching it to your notes, our notes packet got swapped a little bit, so Objective 5 and Objective 6 are switched in your notes packet. So this would correspond in your notes to Objective 5, but in your homework packet it's Objective 6. And specifically for this one, we're going to be doing numbers 8 and 13. And so I've transcribed number 8 here. The directions for both 8 and 13 asked us to solve for theta with a domain of 0 to 2 pi, including 0, not including 2 pi. Okay, and so then you should have already watched the notes video. If you haven't, I would highly recommend pausing this video, going and watching the notes video, coming back to this one once you've kind of been introduced to what we're doing here, because I'm going to be referencing some of the things that are in your notes packet. The first thing we want to do in one like number 8 is step 1 in your notes, which is to isolate the trig ratio. In this one, we only have our 1 trig ratio, and so this one is going to match in your notes most closely to numbers 2 and 3, if you're looking at those in your notes packet. Okay, I'd say most like number 3. So to isolate our trig ratio here, the first thing we want to do is add 8 over to the other side. Okay. And so then we have our 32 cosine squared of 3 theta over 4 equals 0 plus 8 is 8. And then dividing the 32 over, doing that, we get that cosine squared of 3 theta over 4 equals 8 divided by 32 is 1/4. Okay? And so now we are going to take the square root of both sides to get rid of that squared, again further isolating our cosine. And when we take that square root, we need to remember that the square root of our other side becomes plus and minus, as we looked at last semester. Okay? And so the square root of 1/4 is positive and negative 1/2. And that's going to be important because as we consider now what quadrants my angle can lie in, my angle can lie in any of the quadrants. All of them would be viable options because cosine can be positive or negative. So the one thing we do need to ascertain is what is my reference angle for this particular trigonometric expression here, or trigonometric equation. And so my cosine needs to end up equaling 1/2. Okay, so whether you do the hand trick, or you've written out your first quadrant, or you do triangles, or whatever method is that you prefer, all of which again are reviewed in our notes video. Whichever one you prefer, you should end up landing on that the reference angle giving us a cosine of 1/2 is pi over 3. And so then again, because my angle can lie in any of my 4 quadrants, that pi over 3 is my first quadrant angle. The question then becomes, well, what are my second, third, and fourth quadrants, right? Again, if we're picturing our angles here, that's where my cosine would be positive, cosine would be negative in the second quadrant, negative in the third, positive in the fourth. And so then what are each of these angles called? Well, the pi over 3 angle in the second quadrant is called 2 pi over 3. Third quadrant is 4 pi over 3. And fourth quadrant is 5 pi over 3. Okay? So we've done our isolating trig ratio, we've determined our reference angle, and we've identified all of our potential angles. We're on now at step 5 as notated in your notes, which is that we are going to add 2 pi to each angle and repeat as needed to create b pairs of rotated angles. Now, in most of the ones in our notes, we had an integer as our coefficient in front of our theta here. So like number 2 was, I believe, 2 theta, if I remember correctly, so we knew that we were rotating twice as quickly. There was one, I think, that was 3 theta, so rotating 3 times as quickly. In this particular case, I don't have an integer in front of my theta. I have a ratio, right, 3/4. But it's the same idea here. This tells me that I'm moving 3/4 as quickly. And so if I had one full rotation available, I would hit each of these angles. In this particular case, I'm only going to make it 3/4 of the way around, so I know I'm actually going to only hit these first three. And so you could go ahead and cross off that 5 pi over 3 if you wanted. Or if we continued leaving that 5 pi over 3 as is for a bit, you'll actually see why it goes away when we take into consideration our domain at the end, if you prefer to do that. Okay, so personal preference, do whichever one feels like makes the most sense to you. So at this point, we now need to finish solving for theta, and so that means multiplying 4/3 all the way through here. Right, to clear this fraction, so we're multiplying 4/3 all the way through. So my theta is going to equal 4 times pi is 4 pi, 3 times 3 is 9, 2 times 4 is 8 pi, 3 times 3 is 9, 4 times 4 is 16 pi, 3 times 3 is 9, and then you have either crossed off that 5 pi over 3 because of the 3/4 of the way through, or at this point you might momentarily write 20 pi over 9. Right, let me write that over here just because I do tend to cross off the 5 pi over 3, but if say you hadn't, if say you'd written over here 20 pi over 9, well, remember that our domain is only those angles between 0 and 2 pi for theta. So if you include this 20 pi over 9 here, you're saying that theta could equal 20 pi over 9. But the maximum theta can equal is 2 pi, and actually theta can't even equal 2 pi. It actually has to be less than 2 pi. But what would 2 pi be as a 9 in the denominator? Well, that would be 18 pi over 9. So not only can we not equal 2 pi, this is greater than 2 pi. So this is definitely outside of my domain. So even if you had left it in, you would have crossed it off at this point, leaving me with only the 3 answers. Okay? Okay, and then number 13, taking a look at number 13, we have sine squared theta equals cosine squared theta plus sine theta. Okay, so this one in your notes is going to correspond, I'd say, most closely to probably number 6, honestly. Little bit in number 4. Again, just kind of depends on how you see it. Okay, but with both 4 and 6 in your notes, the issue was that we had both a sine and a cosine. Well, we face that same issue here in number 13, which is I have both a sine or a cosine. And so I'm going to be looking in some way, shape, or form to potentially factor this or to do some sort of trig substitution. Okay? Remember that typically speaking, if you're going to factor, we do want to get this equal to 0. So maybe you've subtracted the cosine squared over, subtracted the sine over. And again, there are times where you don't need to get it equal to 0 to factor, but that's a good first step to take. But no matter what you try, factoring just doesn't quite work in this case, and so then you'd be looking at, well, can I substitute somehow? And we know one trig identity at this point. That trig identity that we know is our Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Well, we know other identities, but this particular one is the one that we're going to end up using in this case because we're looking at sines and cosines. Right, so sine squared theta plus cosine squared theta equals 1. And as you're looking at this one, you might initially go, well, I could substitute for either the sine or the cosine because both of these are squared. Okay, but there's something else in this problem that can help you figure out which one should I actually be solving for in this particular case or substituting for. And that other piece is this sine back here. Okay? Yes, I could get sine squared, 1 minus cosine squared, and I could substitute 1 minus cosine squared in here, but the issue would be that I'd still have this sine theta here. Okay, and so what that tells us is because this one is not also a squared, we're probably actually going to want to get rid of this one. Because if I can get rid of the cosine and get this to be all in terms of sine, then I could do some sort of factor, potentially. Okay, so let's go ahead and do that. Again, reminder that because we aren't doing a proof, I can use modified forms of this Pythagorean identity here, so I could subtract the cosine squared over. Subtract the sine squared over. And I can take that 1 minus sine squared and plug it in. And so I get sine squared theta equals 1 minus sine squared theta and then plus that sine theta at the back. And so now we'd be looking to factor, and this is where it's going to look very similar to example 6 in your notes, okay? Which is we're going to get all those signs and look at everything on one side, get this equal to 0. You can technically move either way. I am, in this case, going to add the sine squared over to get me 2 sine squared theta. Subtract the sine theta over, and subtract the 1. Okay, and so now I can factor. Okay, reminder that if you don't like how this looks for factoring, you could, off to the side here, simplify the problem. So 2x squared instead of 2 sine squared minus x minus 1. Ask yourself how that factors, and then substitute sine theta back in. Okay, well, this would factor to 2x, and we want to be multiplying to -2, adding to -1, so this would be +1 and x minus 1. And it's good to always double check. 2x times x is 2x squared. -2x plus x is -x, -1. And then back over here, we use that same factor, but rather than writing x, we write sine theta. Okay. And then solving. We have our 2 sine theta plus 1, which needs to equal 0, and our sine theta minus 1, which needs to equal 0. Okay, and then solving for theta, we're going to subtract 1 on this side, add 1 on that side, so 2 sine theta equals -1, and sine theta equals 1. So this right side's good to go. Left side, we've got one more step, which is I need to divide the 2 over. Okay, and now we have the ability to solve for our thetas here. Okay. So in this particular case, first up, where does sine theta equal 1? Okay, well, we know that that's going to be one of our quadrantals. So the question is, well, which quadrantal has a sine equal to 1? Okay. Well, if you thought through your coordinate pairs, 0, an angle of 0 would be at 1, 0, so sine of 0. Pi over 2 would be 0, 1, so sine of 1. -1, 0, sine of 0. And 3 pi over 2 would be 0, -1, so sine of -1. So in this case, my quadrantal with a sine of 1 would be pi over 2. And then we are only theta, so we don't have to worry about, rotating 2 or 3 times or whatever through our unit circle. So that is my 1 angle. I'm good to go. On the left side, we need our sine to be 1/2, so you're thinking through your hand trick or your unit circle first quadrant, or you're looking at your triangles or whatever method you prefer. The question is, what reference angle gives me a sine of 1/2? Okay, you should have landed on pi over 6. And so then the question becomes, well, what are the pi over 6 angles in my sine is negative, so third and fourth quadrants? Well, the pi over 6 angle in the third quadrant is 7 pi over 6, and the fourth quadrant is 11 pi over 6. And again, we're just theta, so we don't need to worry about multiple rotations, and so we have our answer. Theta is pi over 2, 7 pi over 6, and 11 pi over 6.